Jiang, visiting us from Princeton University. So Yan-Fei did his undergraduate work at Tsinghua University, I know I pronounced that badly, in Beijing. And he's a graduate student at Princeton. He's doing his thesis work with Jim Stone. Like a lot of the Princeton graduates, he's done all sorts of different work with different professors there. He's done some really, I think, nice work with Jenny Green on the observational side, looking at the relationships between, well, looking at the distribution of low mass black holes and galaxies. He's also done some work with Jerry Ostreicher, with Jeremy Goodman, on, for example, on star formation in the outer regions of accretion disks. And then the bulk of his work is his thesis advisor at Jim Stone, who's been on things like radiation, magnetohydrodynamics. And so he's going to tell us about some of this work today. Really exceptionally good research.
Okay, thank you, Jiang. So today I will focus on the new radiation MHD code that developed in Athena. And we applied that code to study the thermal stability and the molecular structure of the radiation-dominant accretion disks. This work is covered by Jim, Shane here, you know people, and Julian and Omer. So the outline here is that I will first the motivation of the project we want to study. Basically, right now, we believe that magnetorotational instability provides a physical mechanism to transfer the angular momentum in accretion disk. So we want to study how the MRI will saturate in the radiation-dominant regimes. This will determine the structure and the structure of the accretion disk. And then we'll describe the new radiation MHD code we developed with Shen, and I will show you a bunch of tasks to show that the code is working as I came. Finally, I will provide code to show some preliminary results when we study the stability and the vertical structure of the accretion disks. So the big picture of the problem here is that if you want to study almost the center of the galaxy of the black hole, when the gas is accreted toward the black hole, it will release the gravitational energy and heat the gas. And in the inner region of the black hole, when the accretion rate is different pressure at the end limit, the gas can be much so hot that radiation pressure can be much larger than the gas pressure. So it can be either in the regime where the radiation pressure is dominant. And another reason that, so in that case, we want to incorporate the radiation field in the dynamics of the flow so consistently, so you can study the behavior of the disk in that regime. Another important reason to do radiation transfer is that because the photons carry the information that we can observe. And then you need to, in order to understand the physical processes in the disk, you want to compare the observations with the spectrum from the disk. So when you do the radiation transfer so consistently, we can generate the spectrum from the disk, and then by comparing the theoretical predicted spectrum with observations, then you can understand the physical process in the disk much better. So I will start with the equations. So there are several things that we want to put in those equations when we study those processes. First is the fluid hydrodynamic, the MHD equations, because we want to calculate the MRI from the simulation so consistently, and then we want to put the radiation transfer in. And because the photons are important not only for the energy budget, but also important for the momentum, so we put in the source current for both the momentum and energy. So the equation here on the left side is the normal ideal MHD equations when there's no source terms. Now we put the energy source terms in, we put the momentum source term in the momentum equations, and the energy source term from the photons in the energy equations. Those equations, and this is we work on the momentum equation of the radiation systems. We solve the two momentum equations for the radiation transfer. This is the dimension disk equation. Don't be confused about the units. So the unit, the capital C here is basically the dimension speed of light scaled by the typical sound speed in the systems. And the capital P here is the dimension number, basically the ratio between the radiation pressure and the gas pressure in the unit. And all those equations are written in the dimension disk form. And here is the source terms for the energy source terms. Here is the momentum source terms. Those radiation subsystems are written in the so-called mixed frame. That means the energy density and the energy flux are in the radial frame, but the opacity are written in the continuum frame. And you can look at this is basically the continuum flux. This is the momentum, the flux term in the momentum substance. And this is the the thermal absorption and emission terms in the energy substance. We include other way of systems like the work done by the radiation force in the energy substance. So this is the fundamental equations we solve. When we put the differential rotation of this, we can calculate the MRI from simulations, and we can calculate the radiation transfer in these simulations so consistently. So then, before we go to describe how we solve the equations, it may be helpful to understand why doing the radiation transfer is hard. Because if you look at the equations, the radiation transfer equation looks much simpler than the ideal equations. You may think it's actually easier to solve, but it's not. The difficulty is that the behavior of the photons can be quite different. Depends on the regimes you are in. That depends on the opacity in the systems. For example, in the very thin regimes, and that means the mean free path of photons is much larger than the typical size of the systems. You basically, the flux is equal to the CLE, and the equation is the wave-like equation. You can describe the photon some kind of wave. However, once you go to the diffusion regime, when the opacity becomes very large, the photons, then the equation, the radiation transfer equation reduces the diffusion equations, like this. And if you go to the dynamic diffusion regime, that means the direction, the motion of the velocity, the fluid is significant. You need to include both the direction of fluid and the diffusion of the photons in that phrase. So it depends on the regime you are in, the properties of the equation to radiation transfer can be different. So we want to develop the mechanism, the algorithm that can work both in the stream regimes and the diffusion regimes, and connect the two regimes smoothly and accurately. And this is important because in the middle plane of the accretion disk, for example, is very often thick in the diffusion regime. But when you go above the mid plane, you can go to the photosphere of the disk. You go to the thin regimes. Then you will need to go to the streaming regimes, and you want to treat that self-consistent and accurately. But because of the difficulty for the property of the radiation transfer, in the previously most people do is just a so-called diffusion approximation. In that approximation, you just drop the DFT terms in the momentum of the photons, and then you treat the flux as just proportional to the gradient of the radiation density, and then you just use the diffusion equation to describe the photons. That is the approximation that most people adopt in the past. And because when you adopt diffusion approximation to the streaming regimes, the signal speed can be much larger than the speed of light. Then you put some arbitrary limiter in your diffusion coefficient. So this is so-called flux limited diffusion approximation. And people know that diffusion approximation is only accurate in very optical regimes, but no one knows when the diffusion approximation will fail or what consequence that will fail. So we want to do something better. Then I will describe what we do with shim and the new method. Basically, we do not adopt any diffusion-like approximation. We use the so-called Godunov method to solve the four two-moment equations of the photons. And the catalytic speed in the photons will change in the diffusion regimes, basically reduced by a factor of 1 of tau, and it can go back to speed of light in the streaming regimes. And also, for the ideality equations, because the source terms become very stiff for the energies. By stiff, I mean that the time scales, for example, the summarization time scales in those terms can be much shorter than the typical sum processing times. And we include those terms in the Godunov method so consistently so that we can describe those dynamics accurately. And we solve those radiation subsystems implicitly, so the time step in the code will only be limited by the sound speed in the systems, because that is the time scales we're interested, and it can be much larger than the photon processing times. So if you notice that in the radiation subsystem, there is always a question that you need to close all the equations by specifying relation between the radiation density and the radiation pressure. So what we do is that we use a so-called variable enhancer based on the module with exchange revive. We basically solve the time-independent transfer equations at the separate part to calculate the specific intensity. And by definition, we just take the angular integer of the specific intensity for the radiation pressure and the radiation density, and calculate the ratio to get the enhancer. Now we can use this enhancer to relate the radiation density and radiation pressure. So overview, the algorithm is that we first solve this based on for given density and temperature of the fluid. We calculate the enhancer based on the time-independent transfer equation. Once we have the enhancer, the momentum equation of the radiation transfer is closed. And then we go ahead with our Godunov method, implicit method, to solve the momentum equation and update the energy density and energy flux, and update the fluid dynamics. And then we can repeat the whole process. That is the basic overview of the numerical algorithm, but in order to show that this is not just a new code, but just it's also a new algorithm. So we developed a bunch of set of tests to show that this code is working accurately for both optically thin and optically thick regimes, and for both the large radiation pressure or small radiation pressure. So we designed the test, span the whole regimes, and show how this code works. The first famous test is so-called shadow test. So basically, the test here is that when you have a white optically thick cloud, mean free path of photon is very short, and then when you share the light coming from the left, so you can imagine, and the ambient median is very optically thin, but the photon mean free path is very long, so you can penetrate easily. So you can imagine that basically what happens should happen is that the light should come in and you should cast a shadow behind the cloud. But when you do FLD, when you do diffusion approximation, because you always assume that the flux is proportional to the gradient of the ER, and the photon can actually change direction. And for diffusion approximation, then you will not get shadow. But because we do not adopt any diffusion approximation, which we solve time-independent transfer equation, for this type, for example, we have two beams come in, and then we can cast a shadow density in the amber and the nebula and form the density behind the cloud. The second test to show dynamically the radiation shock test. So basically when you have a shock coming in, normally you do not consider the effect of the photons. You just have a jump of the density and temperature in the shock regimes. But now when you include the effect of the photons in the upstream can hit the gas in the photons in the downstream can hit the gas in the upstreams, and then actually you can heat up the gas as a precursor before the shock drop. Depends on how large, how strong the photon is, the structure of the shock can change. For example, when the Manhattan number is low, you have a subcritical shock, and the temperature here is smaller than the temperature in the downstreams. But when the Manhattan number is increased, you can have a supercritical shock. The temperature can be increased to the same as this case. And also you have a spike here, it is called Zoltwich spike. It's just an overshoot of the gas temperature and then relax to the downstream temperatures. And then there's a semi-analytical solution by the Rowley and others. And then we can put the semi-analytical solution in the code and test that the code can hold the solution nicely. This is just show the bunch of different structures. For example, when the Manhattan number is small, you have a substrate shock. And then when the Manhattan number is increased, the structure of the shock is also changed. The blue line is the analytical solution, and the black dot are the numerical solutions. And you can see that the code can handle the structure of the shock nicely. When the radiation pressure is strong enough, actually the whole solution becomes smooth again. There's no jump at all for the shock solutions, and the code can also handle that. There is one nice property that I like to show this figure because it's actually nice to illustrate the advantage of the Godunov method very nicely. So basically, in the shock structure, when there's a radiation shock, For example, you can have two fluids colliding and generate the shock. You can show the profiles of the density, temperature, and pressure as a function of the compression ratio. The compression ratio is just the ratio between density at each position of the shock and the density at upstream. And then there is the approximate analytical solution by Godunov in the 1965, I think. And then to predict what structure or profile the shock should be. But in 1996, the sensors use the Zool-like structure code, which use the artificial viscosity to capture the shock. And they find that, the numerical solution doesn't agree with the analytical predictions. And they say that, the analytical prediction is just approximate. Our code is right. But actually, when we do the same thing with our code, with the Godunov method, our code solution actually agree with the analytical estimate quite well. This is because the Godunov method can capture the structure of the shock quite well, but artificial viscosity, you can only get the correct jump, but you cannot get the structure of the shock inside the jump positions.
In the previous plot,
yes.
What determines the thickness of the shock?
You mean the spike?
Well, no, in the right panel. What determines the thickness? I mean, the shock gets wider, basically, right?
I think in the optical depth. Yeah.
It's basically the diffusion line.
Yes. And there's another test we always like to show is that basically the linear wave test. So basically, you can set up a uniform background with uniform pressure, uniform radiation field, and then you just put the perturbation in, and you can linearize your equation to get the eigenvalue and the damping rate of the eigenmode, and then you can put the eigenmode in your code, and you can measure what the damping rate your code will get. And you can measure how the damping rate will converge with the resolutions. And we do that for different regimes. You can change your opacity and different radiation pressure. And our code will converge in both optical thick and optical thin regimes for both large and small radiation pressures. I just jump this place. Okay, that is the end of the introduction of the code. Do you have any questions about code? Okay, then I will go to the most interesting part of the talk, and then the work I'm focused on right now. Now we have the code, so the question we want to study is basically the accretion disk. The basic picture of the basic problem in the accretion disk is that in order to accrete gas inward, you need to transfer the angular moment outward so the gas can get into the black hole. So in 1970s, the people know that the normal viscosity, molecular viscosity is not large enough, so you need some enormous viscosity to do that. And Yang came up with a so-called alpha model. Basically, you assume that the accretion stress in your disk is proportional to the total pressure with some constant alpha. And alpha is assumed to be a constant in the model. And in the local model, so the pressure supports gravity in the locally, and the energy generated in the disk is just diffused out by the photons in the model. Unfortunately, as immediately people realize the alpha model in the radiation dump regime is thermally unstable. This can be understood very easily. So basically, if you can look at the cooling and the heating rate in the alpha model. In the cooling rate for a given surface density, the cooling rate is basically the diffusion is basically proportional to the T force. With the radiation dump regimes, T force is basically proportional to the pressure. But if you look at the heating is basically the integrate the stress and the scale height. The scale height is also proportional to the pressure. But in the alpha model, the stress is also proportional to the pressure. And the heating in the alpha model is actually proportional to pressure as well. So that means if you look at the change of the heating rate on the pressure, that means that the heating rate changes much faster with pressure than the cooling rate. That means you can imagine that very easily that if you start from some equivalent state and you have some perturbation to increase the heating rate, increase the pressure, because the heating rate increases faster than the cooling rate, and then the the heating rate will be larger than the cooling rate. And then the heating will continue to heat up, and then just run away and continue to heat up. On the other hand, if you just decrease the pressure a little bit, because the heating rate will jump faster than the cooling rate, and then the cooling rate will be larger than the heating rate, and the disk will continue to cool down, and the disk will just collapse. So this is the standard thermal instability in the radiation-dominant accretion disks. However, that is the conclusion from the alpha model. And the alpha model, the fundamental assumption is the stress proportional to total pressure. At that time, they did not know what the physical mechanism to generate the stress. So they do not know exactly in physical what the relation should be. Now we know that we believe that MRI, magnetorotational instability, provides stress. So in principle, in the simulations, we can calculate how the MRI saturates and how the saturation state of the MRI will depend on the total pressure. And then we can check whether in the MRI generated disk, whether the thermal instability exists or not. And if it doesn't, we want to understand why it doesn't. If it exists, we want to see whether the MRI provided disk is the same as alpha disk or not. In order to do that, we first start on the local Schrödinger box simulations. That means the picture here, if you have a black hole and you have a accretion disk. Depends on the positions from the black hole. If you are closer to the black hole, you are in the radiation-dominant regimes. If you move out from the black hole, you are in the gas-dominant regimes. The prediction from the alpha model is that the disk is only unstable in the radiation-dominant regimes, and the disk will stable in the gas-dominant regimes. We use the so-called Schrödinger box approximations. So basically, this is the structure of the disk we simulate. We just simulate the patch of the disk, and the photon can dig off from the bottom, from top and bottom of the disk. That is the cooling basically in the simulation. And the MRI will develop in the simulation and will generate turbulence, and then will provide heating. That is the heating side of the disk. So the answer, if the disk is thermally stable, then you can imagine that you get some equivalent that the heating dissipation from the MRI will balance the cooling from photons from the top and bottom of the disk. If the thermal is unstable, then the thermal equivalent can never be achieved. And in the radiation-dominant regime, usually the electron scattering opacity is dominant. When you go further out, the free field opacity, absorption opacity will become more and more important. Just give you a sense of what the simulation can do, because before we talk about the result. So basically, we do the radiation transfer equations, so we can look at the spectrum of the photons directly to see how the photons emit from the disk. The movie here shows just a top patch of one's radiation-dominant simulations. Because we solve both the radiation momentum equation and transfer equations, we can check that the two modules actually give you the consistent result. Here we just show the radiation density. And you can see that during the turbulent stage, the force field just fluctuates along, and the photons, we can calculate the photons coming out from disk, and we can even calculate the spectrum from the disk. This just gives you a sense of what color can do and what information you can get from those simulations.
Just a quick comment. That the thing on the right is the specific intensity. So it's the exact intensity that the particular angle that's being viewed from.
Okay, so now we go back to the result. So the first thing that basically these parameters we adopt. We have focus on the solar mass black hole, and when we show the location close to the black hole, this will be the radiation-dominant case. When we move further out from the black hole, will be in the gas-dominant case. Before I describe my results, at first the previous result working on this is the Horace and the Julian Omer in 2006 and 2009. They also did very similar problems with the Zeus, which used the FLD to capture the radiation transfer. And then very surprised that they find that the MRI, actually the MRI provided disk is thermally stable, because this is one history of different energy budget from their simulations. This is the radiation density, and this is the gas internal density. and this is magnetic density and the kinetic intensity. Over 600 orbits, they do not see any thermal long away in the simulations, and they say that the disk is thermally stable. But this is why surprising results, because they actually find that the structure of the alpha is actually very similar to what alpha disk model predicts, but they do not see the instability. So we want to check the result with our simulations with this new code. The first thing we run is in the gas pressure dominant case. So basically we start up some initial condition with and then we put the seed magnetic field in, and then the MR will be calculated so consistently from the disk, and the disk will turn into turbulence. And when the turbulence is strong, the disk will just heat up. When the turbulence becomes weak, the disk will just fall back. And this is just to show the structure of the disk, of the density from the disk. The right-hand side of the slide, we show the so-called space-time diagram. So what we did is basically we horizontally average different quantities at each height, and then in this coordinate, and show how the profile of different quantities change with the time. So, for example, we look at the density in the gas pressure dominant case. The photosphere is almost at this place, and you can see that when the turbulence develops, the photosphere can fluctuate a lot, can change by even 2 scale height. But the disk is still always stay here. And if you look at the mutual component of the magnetic field, you can see that this is so-called the butterfly diagram in the MRI simulations. You can see that the direction of the magnetic field actually changes directions. The switch signs roughly like 10 orbits in the simulations. This is observed in all the stratified MRI simulations, and it also exists in the radiation case. We believe that this is caused by the dynamo process in the MRI simulations. And we also look at the flux in simulations. When the turbulence is strong, you have more dissipation in the disk. The flux is also increased, the cooling rate is increased. When the turbulence is weak, the flux is decreased. But the bottom line here, the disk is always stable and stay here in the gas pressure dominant disk. We can look at, for example, the box average different terms of the energy, like in the gas density and the radiation density and the magnetic pressure, magnetic intensity. It fluctuates because of the turbulence, but it still doesn't run away, it just stays here, which means that in all simulations, the gas pressure case is still stable. And because we calculate the stress from the MRI simulations, and then we can go back and see how the stress scale with pressure. That means what alpha model will be if you connect the MRI simulations with alpha model. So this is basically these lines. The dominant stress in the MRI simulation is just the maximum stress, and the scale with that pressure is roughly like 0.03. It fluctuates maybe by factor 2, but it's always around this value in the simulations. We can also look at the vertical profiles in those gas pressure simulations. This is done basically in horizontal average and average over different times to see the average vertical profiles of the disk. You can see that within like 3 scale height in the middle of the disk is the gas pressure dominant. But when you go beyond that, it's actually the magnetic pressure dominant in the photosphere in the disk simulations. In this case, the radiation pressure is more, it doesn't dominate and any reduce. And I say that we have the ability to calculate the n tensor from the short characteristic modules, and then we can see how that will differ, like what the profile will be. This is just the horizontal component of the n tensor and the vertical component of the n tensor in the gas pressure simulations. You can see that because in the middle panel of the disk is optically thick, it's actually very close to 1/3, up to like a 5 scale height. And then the vertical component of the n tensor increase to like 0.441 to the top of the distributions, which is consistent with the simple model of the scattering dominant accretion disk photosphere, and the horizontal component drops in this case. So because of the majority part of the disk is critical to 1/3, actually the result, both the vertical structure of the disk, is very similar to the result we get if you just adopt the antenna approximation in the simulations. Okay, this is the gas pressure dominant case. Now we'll go back to the radiation dominant case. So basically what we do here is that we just move out from the disk, and then the vertical gravity of the disk is supported by the radiation. And we can see how that structure will be. This is one simulation that we just throw down, and then this shows the density of the disk. And then you can see the shearing of the disk, and the material in the photosphere just jump in the turbulent mediums. But the more important thing is that if you look at the right-hand side of the disk, this is also the space-time diagrams. You can see that, for example, the density of the disk, it continues to become, the disk, the scale height becomes thicker and thicker with the time going on, until it hit the boundary of the disk. And also, this shows the temperature becomes hotter and hotter of the disk. Especially if you look at the plot-fly diagram in the simulations, the region where the disk becomes turbulent also increase, which means that the region, the stress basically increased when the disk becomes thicker, the disk height is increased. You can also check when you look at the energy budget of the simulations. For example, you can look at the radiation density and the gas density and the magnetic density. You can look at the history. We do not see any thermal equivalent state in the radiation dominant simulations. The disk just run away in the simulations. And you can do the same thing to calculate what the alpha value of the disk is in the radiation dominant genes by calculating the ratio. In this case, is the maximum stress and the radiation pressure. You can see that initially it is maybe 0.02, but actually drops like 0.01 when the disk becomes much hotter in the simulations. So remember, the fundamental criterion for the thermal instability is that the heating rate of the disk will change quicker with pressure compared with the cooling rate. This is the fundamental criterion of the thermal instability, and we can also check that. The red line is basically the heating from the MRI dissipation, and the black line is basically the cooling from the radiation flux. You can see that it is consistent with the previous simulation. With the result is that the heating rate is always larger than the cooling rate.
What are the other contributions to the energy flux, the Poynting flux in the magnetic field, the kinetic energy flux compared to the radiation flux?
In this case, it's always around 1% of the energy radiation flux. So it's a negligible fraction.
And that doesn't change with time.
It actually becomes smaller when the disk becomes hotter. Yeah. So the dominant cooling process is the distribution of flux, radiation flux. The point to take away from this point is that it is true that in the MRI simulations, the heating rate increases faster than the cooling rate, but the slope, how fast the heating and the cooling scale with total pressure is different from what alpha model will predict. The difference between the alpha model predicts that this is 2, this is 1, but the MRI simulations find a much smaller difference. So the growth rate of thermal instability is much smaller than what the alpha model predicts. One reason for that is that, for example, we find that the alpha, the equivalent alpha parameter, is actually decreased with the total pressure becomes larger. But alpha model assumes that the constant.
Is that the Maxwell stress measured at the midpoint or
By the average of the whole simulation.
The whole simulation.
Yes, yes. That's what is used in the alpha model, is the vertical average stress.
And where is the stress?
Sorry?
Where is the stress?
Because it looks like the stress might have been moving up.
Oh, no, the stress basically, the peak like 2 scale, 1, 2 scale from midplane and drops. So it's still, the most dissipation happens in the optic midplane of the simulation. And of course, when the disk becomes a little thicker, the scale height, the size where the dissipation occurs also becomes larger.
But it still stays in the optic.
Yeah, it still stays in the optic reduce. So that is the fundamental prediction of the upper model, is that it is the stress actually, it is the scale height that changes when the pressure changes, which makes the disk
The gravity gets stronger.
Yes, yes. And this is consistent with what we found in the simulations. And if you look at the different energy transfer, how the energy transfer of the disk, actually there are two approaches. The most important is the advection. That when the energy, the radiation is advected from midplane disk, and there is the diffusive flux. In this part shown here, the black line is the Euler flux, which includes the sum of the diffusive emission and advective flux. The red line is the pure diffusive flux, but the dotted line is the contribution from the advection. You can see that at earlier time, when the disk is not that hot, it's still the diffusive dominant everywhere. But when the disk becomes hotter and hotter, the advection actually contributes a significant fraction of the energy transport near the midplane of the disk. But this advection is not included in the alpha model. This will also change the structure on the growth rate of the thermal instability compared with alpha model. And the blue line is the positive flux in the simulations.
Well, I think we can show that if, in fact, you take into account the effects of advection, and say the advection is occurring at basically the buoyancy speed, then you can cure the most important as a matter of principle.
But depends on how fast the advection will be, how significant.
Well,
I think this is in some sense less than, so what you're getting here is a sort of an average effect. So it is less than what you do if you just took the energy and affected it. The flux is quite a bit lower. But it goes, you're right, that it goes in the right way.
At least it's consistent that the growth rate is reduced because of this.
but you may not, of course, have reached that. And you guys may not have reached full limit. It looks like
We're asking, yeah, well, you could tell, like, your energy plot a couple of plots ago. Well, that
almost looks like it's turning over.
It does begin to look
They're
that way.
asking you saturate.
There's several things going on here.
You probably have to talk to your
No,
boss.
the most important thing is reach the size limit of the box.
So what happens if you increase the box size?
We didn't do that, but
But we have done the exercise of changing the box size in other cases, right?
yeah, in other cases, just if it doesn't reach this regime, it will just continue to grow. Right.
So you have done the exercise not for this
not
particular
even
simulation, but you increase the box size and it just grows a little further and fills up the box.
Yeah. But I will say the local simulation is not a good way to study how the thermal instability will saturate. I will comment on that at the end. But another quantity that we can measure is that basically, as I said, the fundamental argument in the alpha model is that the scale height of the disk will increase when the pressure will increase, and then the stress will increase with scale height. And then we can actually measure how the scale height will increase. But you can have different criterion to define the scale height. For example, you can define scale height of the flux, or you can calculate the average MR wavelength, because MR wavelength is the quantity most important for the MR wavelength. And it actually does increase with pressure when the disk becomes thicker. As I said, the thermal instability can go either direction. It can continue to be heated up or just collapse. So this is showed another simulation when we decrease the cell density of the disk and the disk collapse. This part, you be careful to read this part. This line is the total pressure. This is the heating and the cooling rate. So we actually showed how the heating and the cooling rate with pressure during the simulations. So the simulation started with this. So this direction, you can see this region is the earlier like 10 orbit simulation when the MI saturate. And after MI saturate, the disk just collapse. And you can see that the heating rate drops faster than the cooling rate drops. And that's why the disk collapse and the thermal instability exists in all simulations. This is just a consistent that the disk can go either direction in the simulations. And the last point we want to say that in the Holocene 2009, they find that this simulation is stable, and then they give an argument that it is stable because there is a delay between the magnetic energy density and the radiation density, and then why that is called the stable of the disk. However, later people have actually done some analysis to put a time delay in that model, but time delay with like 10 orbit is not enough in the analytical simulations to make the disk stable. And also, we can also calculate the cross correlation between the different forms of energy in our simulations. This is the self-correlation between the magnetic energy density itself. This is the correlation between the magnetic density and the radiation density. And this is the magnetic density and the gas internal density. We can see that in our simulations, we also find there is a delay between the radiation density and the magnetic density. I think this is a fundamental property of the MRI. However, the disk is still thermally unstable. That means the time delay is not the key to make the disk stable. Okay, so the conclusion of the disk simulation that with this new radiation emission code with VT, we find the radiation dominant accretion disk are thermally unstable. However, the growth rate of the MI simulation is much smaller than what half model predicts. And also the direction takes a significant part of the energy transport in the radiation dominant disk. In the future, when the thermal instability exists in the local simulations, a next straightforward question to ask is that how the thermal instability will saturate? Because this is the important question. This will determine the structure of the accretion disk in the radiation dominant case and what the spectrum you will get from those simulations. But the local simulation, because we adopt the gravity, we just assume that the increase continuously with the disk. So it's not good. And also in the local simulations, the surface density doesn't change. In reality, because when the growth rate of thermal instability is so small, actually in the time scale when the thermal instability develops, the surface density at different locations can actually change because it can be comparable to the visible time scales, and that can change how the thermal instability will saturate. All those effects will be studied when we do the global simulations. So that is the next step that we want to do with the global simulations to study the saturation of the instability. And also, right now we just adopt the grid approximation, and then we can use multigroup radiation transfer to do different frequency bands. And because this is the general purpose radiation MHD code, it can be used to study many problems. For example, right now we study that we can actually form the corona, high temperature corona in the accretion disk. And then we can also be used to study the massive star formation in the accretion disk and the aberration of the Jiang cloud. We are working on this with Daniel. And then it also can be used to study the thermodynamics of the proton disks. Just many things that we cannot do right now, and this is a possible future collaborations of this code. Okay, thank you.
So how correlated is the effective energy flux with the magnetic field?
So basically the advection is caused by the magnetic buoyancy is the butterfly diagrams. So it's strongly correlated.
So just to add, so Omer wrote a kind of paper on this in their FLD simulations, and what Yan-Fei sees is very, in qualitative, it's very similar to what they were saying.
Have you seen any trends with resolution, or if you include explicit dissipation, such as a real magnetic random number?
We did do the resolution study. The disk is still somewhat unstable.
And it's always unstable in the same direction.
What was the resolution study? How much resolution?
Oh, the only thing we can offer is first we started 32 per scale height, and then we go to like 64. We cannot go further. It just costs too much computer time. This is the highest resolution we can do. But we do not include the explicit resistivity.
So what's taking up all the time? Is it the rate of transfer?
In the region transfer, either we have to implement, we have to inverse the matrix because we use the implicit method. Right now, like it's almost a factor of 4 slower than the normal Athena code.
But
That's
Actually, I was going to say, that's like almost
well,
like
so the thing is, this is different from what a lot of people do with stratified shearing boxes because they don't have to go 10 scale heights off the midplane. And so, I mean, if you want 64
But
per
you're
H
showing
for 4
that you-
scale heights,
but your results clearly show that it depends on how it
yeah, and so but this is the thing. So doing this boxes that are as tall as Yan-Fei is doing is just much harder, even with just MHD.
For example, in the earliest simulation that Julian Bowman did, they used only like 0.5 scale high in the x direction and 2 scale high in the vertical direction, in the azimuthal direction, and like 4 scale high in the vertical direction. What the simulation we did with like 1 scale high in the x and 4 scale high in the azimuthal, and we can go like 10 scale high in the vertical direction. When we increase both sides, and if you go to like 128 degrees, I cannot fit that simulation for my thesis, so we just cannot afford that.
So maybe I missed this point, and you said something to this effect, but what is the fundamental difference that causes the change in thermal instability between flux limited diffusion and variable
That is-
energy tensor?
It's a very good question.
Or maybe you don't know the answer, which is fair.
So basically, the answer, we do not know the answer. We first,
What would he suspect?
we initially suspect it because of different treatment of the radiation, like FLD and VT. But actually, recently we did a task, we implemented FLD in Athena, and it's still unstable.
Oh.
Yeah, Yan-Fei went to implement flux limited diffusion, which is a huge project, just to check. And it's still unstable.
It doesn't, that's the radiation
Well, it's a different. You can't do them exactly the same, right? So flux limited diffusion and Athena is not identical to flux limited diffusion in Zeus, but they look very similar at the start.
But they're doing totally different things than some things.
It's just to say that the thermal instability is very, the instability is sensitive to many detailed things that we do not understand right now.
I mean, the reason I asked is because you showed the difference in the energy tensor was primarily in the corona, which is where not most of the dissipation.
Yeah.
And so, I mean,
That's
why I was very
Yeah.
confused. So.
But downside right now we do not know. But at least we understand our simulation is certainly unstable, and we understand why it's different from what other model predicts.
Well, what's going to happen? And I actually thought through this when I was a postdoc during this fellowship. If you have magnetically driven point transport of the radiation, you can work out a simple equivalent to this model. And in fact, you can show there is a characteristic depth of the in the disk below which advection dominates over diffusion as alpha depth diffusion takes over, and it's stable. So it looks like you just haven't quite reached that, and wait a little bit longer, you'll see the equilibrium.
Well, he's got to make flux bigger than
But he looks like he runs it a little bit more, right? It's the effective flux.
No, but what he's saying is that it's rolling off because it's hitting the top of the box.
Right.
That's why it's seeming to roll off. So, and they did the experiment where they changed the height, and when it was unstable for longer, it just falls until it hits the box. So you don't know yet.
Wow.
No, they're telling you that's what the result is.
And also, for example,
It looks like the effective flux is going up. You showed us.
yeah, the vacuum flux does go down,
So
but
it goes up and down. It should quite check.
But right now we don't know, because also when we reach 10 scale height, the local simulation is not good because the position of the disk is only the radius of the disk is only like 10 times of the scale height of the disk, or even 20. And then when you reach 10 scale height, you almost the scale height is almost the same as the position.
I see. You're saying that it's already got geometrically thick.
It also reach the limitation of the local simulation.
Oh, for the realistic parameters that you were putting in.
Yeah. So that's why Another reason that we want to do global simulation to study the saturation of the disk.
So at the end of the day, what was your H over R for the plasma between the
In the model, we assume that the R is like, I think that about 30, about 1 or 1/3 at the end of it.
Oh, 1/3.
Yeah.
So,
The gamer shuts off.
More questions? I would like to ask a question. So, I'm sorry, but I know this is a question. How does it depend on the radius? So if you increase, you just said you're doing spinning boxes, but if you increase the radius in the radial direction, how does instability, is it still unstable? Or
It's still unstable, yes.
and how does the growth rate of it vary?
Right. Actually, I think that if you do the same resolution when you change the box size, actually if you just change the radial side, it actually the growth rate doesn't change too much. But if you change the mutual size, the heating will become a little bit strong initially, but eventually it's still unstable. It either be collapsed or just dissolved.
Well, maybe one quick last
One last.
How strong is the magnetic, seed magnetic field you're choosing? And have you checked how your instability results depend on that?
Yeah, we try different bunch of initial magnetic field. For example, the beta parameter, or the ratio between the initial magnetic field and the gas pressure, we change like from 10 to like 30, and from like 5. It doesn't depend on that. This is still unstable because the MRI very quickly amplify the magnetic field and will get to whatever it wants in the saturation state.
Yeah,
Because
is it in the saturation state?
but the saturation in beta, it depends on the regimes. So basically, in the radiation down regimes, the magnetic field, for example, the magnetic pressure can be actually larger than the gas density. In the gas pressure case, magnetic pressure is smaller than the gas pressure. But it's always a fraction of it's a small fraction of the total pressure.
All right.
You can ask.
We'll take it with these. So Yan-Fei is going to be around tomorrow, and the rest of the day, if you'd like to talk to him, we're going to be taking him out to dinner. So let me know if you want to join us. Thank you again.